Hi everyone, this is lesson 2-5, Rational Functions video for 251 and 252. Our learning target for this video will be for students to be able to find vertical and horizontal asymptotes and graph rational functions. So let's talk about vertical and horizontal asymptotes. The vertical asymptote of a function is the line x equals c of the graph f if the limit as x approaches c from the left is equal to positive or negative infinity, or if the limit as x approaches c from the right is positive or negative infinity. So if you look at this graph in the example, we have a vertical asymptote here at x equals -2. And you can see that as we approach that x equals to -2 from the left, we have an end behavior right here that's going towards infinity. And as we approach -2 from the right, so as I come from values greater than -2, our end behavior is also approaching infinity. So since our end behavior is infinite when we approach -2 either from the left or from the right, we can say that there's a vertical asymptote at -2. Now the other way you can look at this is if I write out the function as 5 over x plus 2 times x plus 2, and in that then the denominator is the domain is restricted because the denominator cannot equal 0. So we know that from finding the domain, x plus 2 can equal 0, which implies x cannot equal -2. So since x cannot equal -2, that implies that a vertical asymptote exists at -2, and the only reason it is a vertical asymptote is because we are dividing by a factor of x plus 2, which eliminates -2 from being a part of our domain. So the definition we have up here in words is that if the end behavior is infinite, either approaching positive or negative infinity from the left of a value or from the right side of a value, of an x value, then you have a vertical asymptote. Algebraically speaking, when we talk about an asymptote, we can find a vertical asymptote when a factor of our domain, or a factor of our denominator, produces a 0, in which case that x value has to be restricted from our domain. So if I were to write the domain for this function, just to tie this to some things that we've already talked about, this is -infinity to -2, union -2 to infinity. Now, in words, for a horizontal asymptote, the line y equals c is a horizontal asymptote of the graph of f if the limit x approaches -infinity of a function is equal to c, or if the limit as x approaches infinity of a function equals c. So if you are finding the end behavior of a function, so letting x approach positive infinity or letting x approach negative infinity, going to the right infinitely or going to the left infinitely, and the graph is leveling out, such as it is here, right? We have this huge line right here at y equals 6, right? Because our horizontal asymptote is at y equals 6. We can determine that horizontal asymptote, what the value of it is, by determining the end behavior of our function. The best way to determine when your end behavior is approaching a constant is by using the table function either in Desmos or in your graphing calculator and letting x get really big. So earlier in the year we did something with tables, letting x go from 100 to 1,000 to 10,000 to 100,000, etc. And what you'll see in this particular example for a horizontal asymptote approaching our horizontal asymptote at y equals 6, is our limit will approach 6. So what you'll see here is probably like 5.9, 5.99, 5.999, 5.9999, etc. And you can see these values here, as x gets larger, are approaching 6. Eventually, if you put in enough zeros here, if you just put a bunch of zeros in your table behind or after a 1, you will eventually see 6 as your y coordinate. Now, if we're looking at the equation, if we're looking at this from an algebraic standpoint, a horizontal asymptote is found if you take the highest degree term in the numerator and the highest degree term in the denominator, and you compare them. Okay, if you compare them, if your degrees are the same on top and bottom, then you divide your coefficients of those terms, so 6 divided by 1, that gives you your horizontal asymptote. So if your degrees are equal, then you take the coefficients of those terms and divide them, and that gives you your horizontal asymptote. Now, if your degree is larger, let's say we had an x cubed on top and an x squared on bottom, our degree is larger in the numerator than in the denominator. There is no horizontal asymptote then. If our degree is higher on top or on bottom than on top, so if we had x squared over x cubed, for example, then our HA, our horizontal asymptote, is y equals 0. So the end behavior of the function would approach y equals 0. We'll be approaching the x-axis. So I just wanted to explain those 3 scenarios there. You can definitely find the horizontal asymptote by determining the end behavior of the function, or you can use these rules here. If your degree is the same on top and bottom, then you divide the coefficients. If your degree is higher in the numerator than in the denominator, there is no horizontal asymptote. And if your degree is higher on bottom than on top, so higher in your denominator than in your numerator, then your horizontal asymptote is at y equals 0. Okay, so we're going to find the vertical and horizontal asymptotes of this function. We're going to find the domain of f of x equals x over x minus 1, and the equations of the vertical or horizontal asymptotes, if any. So what we're going to do is, first of all, find the domain of this function. So first of all, since it's a fraction, I know that x minus 1 cannot equal 0. Because the denominator can never equal 0, that implies that x cannot equal 1 if I add 1 to both sides. So since x cannot equal 1, the domain of my function then is negative infinity to 1, union 1 to infinity. Now, also because x cannot equal 1, we have a vertical asymptote in our graph at x equals 1. So our vertical asymptotes are actually found by determining what x values are restricted from your domain, but more specifically, the vertical asymptotes are when one of the factors in your denominator creates a 0. So wherever your denominator is equal to 0, that is where the graph of the function is going to have a vertical asymptote. So vertical asymptote occurs in this example at x equals 1. Our horizontal asymptote, I can use either the end behavior of the function, so I could graph this function and determine the end behavior, or I can compare the degree of the numerator and the degree of the denominator. So at x equals, or x to the first power on top, and we have x to the first power on bottom, So if you look at the highest degree term in the numerator, it's x to the first. And the highest degree term in the denominator is also x to the first. So what we should see then when our degree is equal, when our highest exponent is equal on top and on bottom, then we take the coefficients of those terms, so 1 and 1, and we divide them. Okay, I'm taking a positive 1 here and a positive 1 here and dividing them. That gives me 1, which means that we have a horizontal asymptote at y equals 1. So looking at the graph of the function, a reminder that we had a function of x over x minus 1. And if you look at the graph of the function here, I'm just going to confirm, we do have a vertical asymptote at x equals 1, right? And we have a horizontal asymptote at y equals 1. So if you were to find the end behavior of this function, and you look at the end behavior of this function, we have as x approaches infinity, as x goes to infinity, as our limit, the limit of the function as x approaches infinity, gives you a y coordinate of, not 0, my bad, of 1. Okay, and if you look at the other side of the graph, if we determine our left end behavior of this function, the limit as x approaches negative infinity of this function is approaching 1 as well. Now, I could confirm this with a table of values, but if I just trace this piece of the function and I'm going all the way towards negative infinity, then our y coordinate then is approaching 1. Same thing on the right side. If we approach positive infinity here, then our graph is flattening out and you can see that it is approaching a y value of positive 1. Now again, we could confirm this in a table of values. Like I said on the last slide, you can let x approach positive infinity or x approach negative infinity by letting x get super big in your table, or let x get super big negatively in your table, and you can see that your y coordinate is going to be approximately 1. Alright, we're going to take another look at a different example here. Finding the domain of the function f of x when f of x is equal to 4x squared plus 3 over 2x squared plus 1. And the equations of the vertical or horizontal asymptotes, if any. So, we're looking at three things. Find the domain first. Then we will look at the vertical and horizontal asymptotes, if there are any. So first of all, the domain of this function can be determined because this is a rational function, a fraction of two polynomials, one polynomial, a quadratic polynomial on top, and a quadratic polynomial on bottom. Since we're dividing those two, we always know that the denominator can never equal 0 in a function. So we have 2x squared plus 1 cannot equal 0. So when I solve this equation for x to find the restrictions on our domain, I start by subtracting 1 on both sides. So 2x squared cannot equal negative 1. If I divide by 2, I get x squared cannot equal negative 1/2. And because this is x squared cannot equal negative 1/2, and a squared value can never equal a negative number, because if I were to square root both sides of this, I would get x cannot equal plus or minus, let's see, square root of 1/2 is 1 over the square root of 2. So plus or minus 1 over the square root of 2, because this right here, we put a plus or minus because a positive and a negative squared could give me a value. However, because this is negative underneath the square root, the solution is imaginary. So here's the deal though. There's no x value that's squared that is going to give me negative 1/2. Thus, there are no restrictions on our domain. There is no x value that's going to create a 0 in our denominator. So our domain in this case is all real numbers. Since, again, there's no restrictions on x, there's no x value that is going to give me 2x squared plus 1 equal to 0. Now, for vertical and horizontal asymptotes, because there are no restrictions on my domain and I am never going to divide by 0, that means that there are no vertical asymptotes for this function. Now, as far as our horizontal asymptote goes, we can still have a horizontal asymptote even though there's no restrictions on our domain. And again, the horizontal asymptotes can be found by either finding the end behavior or by dividing the highest degreed term in the numerator by the highest degreed term in the denominator. So the highest degreed term, the term with the highest exponent in the numerator, is 4x squared, and in the denominator that would be 2x squared. And since our exponents are equal, okay, the only time we need to divide those two values, divide the two coefficients, is when the degree of the numerator and the degree of the denominator are equal. So here I get 4 divided by 2, which is equal to 2. So we have a horizontal asymptote right here at y equals 2. Now what this means is that when I determine the end behavior of this function f of x, the graph is going to flatten out at the ends as I approach infinity and also when I approach negative infinity, and the y-coordinate that it's approaching is 2. Hence why we have a horizontal asymptote at 2. So I'm going to go ahead and graph this on the next slide, and we can look at the fact that our domain is all real numbers, or negative infinity to infinity, that we have no vertical asymptote, and that our horizontal asymptote is 2. Alright, so here is the graph of our function f of x from the previous slide. And what we want to look at here is the fact that we stated that the domain was all real numbers. Now, if you look at this function, here at the graph of this function rather, you can see that this function, if I trace it from left to right, is continuous. There's no gaps or breaks in our graph. We never have to lift up our pencil, which means our domain is all real numbers. So again, our domain stretches from negative infinity all the way to positive infinity, which means that there's no vertical asymptotes on our graph. Again, we never have to lift our pencil when we're sketching this function. So there's no break or vertical asymptote. However, there is a horizontal asymptote. If you notice, if I draw this line, and it's not real straight, I'm trying my best here on the iPad, but this equation of this line is y equals 2. And if you were to trace the function and determine the end behavior of this function, as x gets closer and closer and closer to infinity, so as I move to the right infinitely, the graph levels off and approaches a y value of 2. And if I do the same on this side, as x approaches negative infinity, the graph levels off and approaches a y value of 2. So that is helping us determine, again, the end behavior helps us determine whether or not we have a horizontal asymptote. In order to have a horizontal asymptote, your end behavior has to approach a constant, an actual number, and it cannot be approaching infinity or negative infinity for a y value. Alright, so we're going to check your understanding here of the domain and vertical and horizontal asymptotes. I want you to find the domain of k of x equals 5x plus 10 over x minus 4 and find the equations of the vertical or horizontal asymptotes if the function has any. You have 4 choices, A, B, C, or D. So go ahead, work out the problem, and press submit when you have your answer. Okay, so we're looking at the domain of this function, k of x. Again, it's a rational function because we're dividing two polynomials. We're dividing a degree 1 polynomial on top because our exponent in the numerator is a 1. Highest exponent is 1 here. Highest exponent is 1 on bottom. So we're dividing two polynomials or two linear functions, which makes it a rational function. Now, what we want to determine is the domain. Well, we have known since chapter 1, the beginning of chapter 1, that we can never divide by 0. The denominator of a function can never equal 0. Therefore, x minus 4 can equal 0, which implies x cannot equal positive 4 if I add 4 to both sides. So my domain is all real numbers with the exception of 4. So looking at the multiple choice question, or multiple choices over here, I am going to look at a domain, or look for a domain that says x cannot equal 4, excuse me. So B is out because in B it says the domain cannot equal 5. And D is out because it says that x cannot equal 4, and then my guess is this is supposed to be a negative 4 right here, but they never put that. So when we're looking at the function here, we have two choices, A and C, and we're going to determine our vertical asymptote. Well, our vertical asymptote is whenever the function is dividing by 0, in which case the vertical asymptote is always going to be the x value where your denominator or your function is equal to 0. The denominator in your function is equal to 0. So wherever x minus 4 is equal to 0, which is at x equals 4, that is where our vertical asymptote is. So we're going to have a vertical asymptote at x equals 4. And our horizontal asymptote can be determined either algebraically or graphically. Algebraically speaking, because the degree of our numerator, because our degree is 1 on top and our degree is 1 on bottom, because the degrees are equal, we divide the coefficients. So we have a 5x on top and a 1x on bottom. Since our degrees are the same here, we divide the coefficients. So 5 divided by 1 is equal to 5. So our horizontal asymptote is going to occur at y equals 5. Now what this means graphically is that when I determine my end behavior, when I find my limit as x approaches infinity, I get 5. And when I determine as x approaches negative infinity, the left end behavior, that is also going to approach 5. So looking at A and C, A says the horizontal asymptote is at negative 10, which is not true. So A is not my response. And C, because C says that the horizontal asymptote is at 5 and that a vertical asymptote is at 4, is the correct response for this question. All right, I've graphed this function here, f of x. I'm just going to confirm our answer graphically, that we have a horizontal asymptote at y equals 5. So right here, we're going to have a break in the graph horizontally, which means that in our range, y cannot equal 5. And vertically, a vertical asymptote at x equals 4, which is right about here. So we can see on the graph that our graph is restricted, our domain is restricted at 4, and our range is restricted at 5. And if you were to determine the end behavior of this function graphically, you can see that as x approaches infinity, the y value is approaching 5. And as x approaches negative infinity, as I trace the graph to the left infinitely, the graph is also approaching 5. So your end behavior or your limit as x approaches negative infinity and the limit as x approaches positive infinity would both be equal to 5 in this example. All right, so looking at graphs of rational functions, which we've already been doing in the previous examples, we're going to give a formal definition, I guess, of vertical asymptotes and horizontal asymptotes, and also talking about the intercepts, because we're going to start graphing these functions based on where the vertical and horizontal asymptotes are and where the intercepts are. Now, a rational function is two polynomials divided by one another. So you could have a quadratic divided by a linear function, a cubic divided by a quadratic, etc. One thing they express is that b of x cannot equal 0. The bottom function can never equal 0. And also a of x and b of x, the two functions, can have no common factors other than plus or minus 1. And then the graph of f has the following characteristics. So you don't want a common factor, like if you factored the polynomial on top and factored the polynomial on bottom, you wouldn't want the two polynomials to have any factors in common. Otherwise, they would just cancel each other out. So our vertical asymptotes are occurring when b of x, when that bottom function is equal to 0. And again, there's summarizing here the horizontal asymptote, which we said before we can determine by using the end behavior, or there's three scenarios that play out. If your degree n is less than your degree m, so in other words, your degree on top is greater than your degree on bottom, then your horizontal asymptote is at y equals 0. Sorry, if your degree on top is less than, less than, n is less than m, so top degree on top is less than the degree on bottom, then your horizontal asymptote is at 0. So the graph is going to approach the x-axis at the ends. If n is equal to m, we divide the coefficients of the highest degree terms, which we've done that a couple times now. And then if our degree on top, if the degree on top is greater than the degree on bottom, then there is no horizontal asymptote then. Okay? So if I had an x cubed function divided by an x squared function again, this degree is 3, this degree polynomial is 2 on bottom, and when the degree on top is greater than the degree on bottom, there is no horizontal asymptote for the function. Now to summarize intercepts, we've talked about x and y intercepts all year. The x-intercepts are the real zeros of the function. So whenever the top function is equal to 0, those are your x-intercepts. Your x-intercepts can be determined by determining the zeros of the top function, or the zeros of the numerator. The y-intercept exists if the value of f is when x equals 0. The y-intercept is when the value of the function f when x equals 0. Okay, so again, finding the y-intercept, how do we find the y-intercept? We substitute x equals 0 into the function and solve for y, or find y. Okay, so we're going to graph rational functions here. So in order to graph our function, we are going to find all those key components that we discussed earlier, the domain, the vertical asymptote, horizontal asymptote, and now they're going to also add in the intercepts. So first of all, I'm going to find the domain of this function first because it asks us to state its domain. I know that x plus 5 cannot equal 0, which implies x cannot equal negative 5. So my domain is going to be from negative infinity to negative 5, union negative 5 to infinity. I also know because negative 5 is restricted from my domain that my vertical asymptote is at negative 5. That's where the break in my domain is. Anytime we divide by 0, that causes a vertical asymptote in our graph at that particular x value. Our horizontal asymptote, because we have no x in our numerator, this is really 7x to the 0 power, and we have 1x to the first power. Anytime our degree, so highest exponent, is higher on bottom than on top, so we have a degree 0 polynomial on top, and we have a degree 1 polynomial on bottom, when this degree is greater, when the highest exponent on bottom is greater than the exponent on top, then we have a horizontal asymptote at y equals 0, which just so happens to be the x-axis. So we already know that when I graph this function, or when we graph this function, the graph is going to level out at the ends, and it's going to approach the x-axis as x approaches infinity and as x approaches negative infinity. So we have our horizontal asymptote, we have where our vertical asymptote is. I want to know where our intercepts are. So our x-intercepts are when the function, the top part of the function, of our rational function, so the numerator is equal to 0. Well, since our numerator is 7, 7 can never equal 0, which implies that since we have no x value in our numerator, the numerator can never equal 0, which implies that we do not have an x-intercept. Okay? Because 7 cannot equal 0, since the numerator can never equal 0, that implies that this function, k of x, does not have any x-intercepts. Now, our y-intercept can be found by plugging in 0 for x. So if I plug 0 in for x, I get 7 over 0 plus 5, which gives me 7 over 5, which is going to give me 1.4. So our y-intercept, our y-intercept where x equals 0, is going to occur at y equals positive 1.4. So here's what I'm going to do. I'm going to go ahead and graph this function using all these key components, putting in our vertical asymptote, our horizontal asymptote, and then our y-intercept. Alright, so I'm going to sketch this graph. I know that this function has a y-intercept at positive 1.4. So I'm going to plot a dot on the y-axis at 1.4. At 1, 2, 3, 4, 5. At negative 5, I have a vertical asymptote. And we know that our horizontal asymptote is at the y, or at the x-axis where y equals 0. So really I'm just going to put this dotted line over the top of the x-axis as a guideline for my horizontal asymptote. And when I graph the function, I'm going to pick some additional points. And so to pick some additional points, I have to plug in x values for other x values for the function and then determine what the y coordinates are. So just looking at some options here, I know that the graph, let's try x equals negative 1 and x equals positive 1, so I can see what the graph is doing in this region here. Okay, so if I plug in negative 1 and positive 1, I get 7/4 and 7/6 as my values. And so I know that the graph is going to look something like this. The graph is going to come down and approach the x-axis because it's going to approach the horizontal asymptote. And if I plugged in negative 6 for x and found my y value, I would get negative 7. So what that tells me is the graph is going to look something like this, because at negative 6 we'd be way down here at negative 7. And again, this is just a sketch of the graph. If you want a more exact graph, you could go ahead and graph this on Desmos, and it would look something similar to what I have graphed here. The main idea here is that you are identifying the key components, which are the x and y intercepts. Again, this graph never crosses the x-axis, so we have no x-intercepts. We did have one y-intercept at 1.4, which a function can only have one y-intercept anyways. And we determined we had a vertical asymptote at negative 5, right here, negative 5. And we had a horizontal asymptote at 0, which is the x-axis. All right, so here is a little better graph of the function. You can look at the fact that we have x equals -5 as our vertical asymptote, that the graph levels out at the ends and approaches the x-axis, which is y equals 0. So here's our horizontal asymptote. Here's our vertical asymptote at -5, which is x equals -5. And you can also see our y-intercept right here at y equals 1.4. And you can see that the graph actually never crosses the x-axis. It skims it, it approaches it, but it never actually intersects it. All right, so for example B, we have the function f of x equals x plus 1 over x squared minus 4. Same idea here. We're going to determine any vertical and horizontal asymptotes if they exist, as well as the intercepts, and graph the function and state its domain. So I'm going to always start with the domain. That tells me where my denominator is, my restrictions for my domain is where my denominator is equal to 0. So I'm going to state that the denominator cannot equal 0. That implies x squared cannot equal 4 if I add 4 to both sides of the equation. So plus 4 and plus 4 here. And when I square root both sides, I get x cannot equal plus or minus 2. So I have two different values here. I have two different restrictions, one at positive 2 and one at negative 2. Positive 2 and negative 2. And if you look at then the vertical asymptotes occur whenever our function divides by 0. And so we will have a vertical asymptote at positive 2 and at negative 2. So wherever our domain is restricted, or whenever our function is dividing by 0, okay, those create vertical asymptotes in our graph. So we have a vertical asymptote at 2 and negative 2. As far as a horizontal asymptote goes, if I look at the degree of the function, the degree on top is 1 and the degree on bottom is 2. Since the degree on bottom is greater than the degree on top, that implies that the horizontal asymptote is at the x-axis, which is the equation y equals 0. So we know by this information here, at the horizontal asymptote, that when we look at the graph, at the ends, when x approaches infinity, and as x approaches negative infinity, the y-coordinate is approaching 0. As far as our intercepts go, our y-intercept is going to be when we plug in 0 for x. So if I plug in 0 for x and evaluate the function, you get 1 over negative 4. So we get a y-intercept at negative 1/4. And our x-intercepts, our x-intercepts occur when the top function is equal to 0. So when the top function equals 0, which occurs at x equals negative 1, that gives us our x-intercept, or the zeros of our function. So this equation or function has an x-intercept at negative 1, a y-intercept at negative 1/4, a vertical asymptote at both 2 and negative 2, and has a horizontal asymptote at y equals 0. Alright, so I've graphed the function on Desmos. As you can see, we have two vertical asymptotes. One occurs at 2, one occurs at negative 2, and the graph here approaches, as x approaches infinity, the y-coordinate is approaching 0, and as x approaches negative infinity here, the y-coordinate approaches 0. So we have a horizontal asymptote right here over the top of the x-axis, which is at y, sorry, my bad, gotta erase that, y equals 0. Here we have a vertical asymptote at x equals 2 and x equals negative 2. and our y-intercept, again, occurred at negative 1/4, and our 1 x-intercept occurred at x equals negative 1. So right here you have x equals negative 1. Right here you have a y-intercept. You're crossing the y-axis at negative 1/4. All right, so here's what I want you to do. I want you to check your understanding of vertical and horizontal asymptotes and intercepts for this function. And it doesn't say provide a graph, but it wouldn't be a bad idea for you to just graph this function to confirm your answers, to make sure that your vertical and horizontal asymptotes are in the correct location as well as the intercepts. So go ahead and work this problem out and choose A, B, C, or D, and then press submit. Okay, so we are going to take a look here. Our vertical asymptotes are going to occur when the denominator is equal to 0. Because this polynomial is not factored, I'm going to go ahead and factor this polynomial. So this polynomial, this quadratic, factors into x plus 4 and x minus 3, because positive 4 times negative 3 gives me negative 12. And when I add 4 and negative 3, I get a positive 1. So that implies that x, if these values cannot equal 0, then that means x cannot equal negative 4, and x cannot equal 3. So since our domain cannot include negative 4 and positive 3, that implies our vertical asymptotes are at negative 4 and 3. So if I look at my choices here, that eliminates C, and that eliminates D. And now what we need to do is we need to look at any possible horizontal asymptote. So our horizontal asymptote considers the degree of the numerator and the degree of the denominator. Since I do not have a x value, really this is x to the 0 power next to the 1 on top. I have an x squared on bottom, and since the degree is greater on top, since my exponent is greater on, I take that back, since my exponent is greater on bottom than it is on top, right, 2 is greater than 0, that implies that our horizontal asymptote is at y equals 0, or the x-axis. So looking at A and B, they both state, actually, example B or choice B says the horizontal asymptote is at 1, which it is not. We now know that our answer is A. However, I have not discussed the y-intercept. The y-intercept is found by calculating the is calculated by plugging in 0 for x. So I'm going to find m of 0 equals 1 over 0 squared plus 0 minus 12, which gives me 1 over negative 12. Now, if I divide 1 over negative 12, that's going to give me this decimal right here, negative 0.0833. And you might be wondering why they don't say anything about an x-intercept. That is because this function does not have an x-intercept, because the x-intercept is found when the denominator is equal to 0. Well, if I set 1 equal to 0, 1 can never equal 0. So if you do not have an x variable in your numerator, you will not have an x-intercept to your function. So that is why none of these choices mention an x-intercept, is because there isn't one.